Today's quiz is really a math quiz, and it's going to ask us to think about what numbers mean. Most of us assume arithmetic always works. That's the question we're asking. Does arithmetic always work? Here's how I have this worded. It says, is a number plus another number ever itself? That gets to the heart of our issue. As always, write down your thoughts as completely as you can, and then mark your confidence on what you think about your own answers. Come back to this. Typical student answers normally include, arithmetic always works. Of course, 1 plus 1 always equals 2. Some will even go so far and say, it's a fact of nature. We didn't make math up. If I have one golf ball and I have another golf ball, I now have 2 golf balls. Must be true. Others will say, I'm suspicious of math. I think it was made up, and I'm not really sure. And others will say, I've taken a little bit of physics and I realize sometimes things get a little bit complicated. Those are the most typical responses that we get. But usually, most will say, of course, arithmetic always works. When we go to explain arithmetic to children, we use very simple examples. However, some examples can get complicated. Let's go right to a real-world example. Einstein developed an idea of relativity, and he essentially stated that when objects are moving, their time seems to be different than other viewpoints or frames of reference. He gave us a correction factor to get the two times to speak to one another. We don't have to worry too much about the relativity right now. We can simply look at the equation. This is going to lead us into what we're really talking about today. So if we write down gamma is that correction factor. It's a simple piece of algebra. Gamma equals 1 all over the square root of 1 minus v squared all over c squared. V is a velocity. We can think of that as being the speed. C is the speed of light. Let's go ahead and define both of these. Speed of light is very fast, as most people know. I'll write it out for us. C is equal to 300 million meters per second. In Einstein's day, 10 meters per second would be a more typical speed. So let's talk about something that's going at a velocity of 10 meters per second. Maybe a car or a carriage or something like that. That's about 22 miles an hour, something like that. So if I had some kind of carriage or cart and a person is standing on it and they're going with a velocity of 10 meters per second. We can put both of these values into this equation. That's what we're going to do now. We're going to find out how arithmetic works. One of the interesting things is Einstein didn't have a calculator, so he'd have to do this kind of work by hand anyhow. Let's just jump right in. The numbers are going to get big, and we might have to bring a little bit of algebra in, but we should be okay. Gamma equals 1 all over. Let's put our numbers in. Let's take the square root of 1 minus our 10 meters per second. I need to square that, all divided by our c squared, which would be this value. Now, just so you know, this value can be written in an easier form. I can end up writing this as 3 times 10 to the 8th meters per second. I can do it either way. So I can write this one as 3 times 10 to the 8th meters per second. And I need to square that. So this is going to be a pretty big value on the bottom. Let's go ahead and do it. So gamma is going to be equal to 1 all over the square root of 1 minus, and that would be 100 meters squared all over seconds squared. All over. Now, if we wrote this out, it's going to be a very, very, very large number. So I'm going to leave it in this exponential notation. And in case you didn't know, when I square a value, this is a squared function, I'm going to take, this is an algebra thing, where x to some number, let's say n, and if I raise that to another power of m, I could say that's equal to x n times m. I just multiply them together. So the 2 and the 8 would make 16. So I'd end up having 9 times 10 to the 16th, and that would be meters squared seconds squared. Notice our seconds squareds and our meters squareds are going to leave us. We can cross those out. Now we can really just focus on these numbers, which is going to be a trip anyhow, because this number is really, really large. Now, let's just take a little aside here and understand that when I have 10 to the 8th, what that really means is I have 8 zeros after my number. So I've got 1, 2, 3, 4, 5, 6, 7, 8. So 8 zeros after my 3. Right here, I could say I have 9 with 16 zeros after that. Let me write that out. Gamma equals 1 all over the square root of 1 minus 100 divided by 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's hard to write these long numbers out. This is really going to be difficult to work with. I'm going to have to take this up here. Hopefully I have enough room. Let me go move my camera. I want to make our life a little easier. You might not think it's going to be easier, but this 9 is almost 10, and I'd rather make these ones and zeros. So I'm going to approximate just a little bit. I hope that doesn't throw anyone off. So this can also be written as 9 times 10 to the 16th. If I push it over just a little bit, that can be 10 to, or 1 times 10 to the 17th. So it'd be 10 times 10 to the 16th. I can shift everything one place and make this equal to 1 times 10 to the 17th place. Let's just play along. The bigger picture here is playing with numbers. So I could then say gamma is equal to 1 all over the square root of 1 minus 100 all over that big, huge number of 1 times 10 to the 17th. And I rounded a little bit. And I know that's going to be a problem, but now we're really into the essence of what these numbers mean. I can also write 100 as 10 to the 2nd. Let me show you. If I had 10 times 10, that's the same thing as writing 10 to the 2nd. 10 twice. So I'm going to replace this and write this as gamma equals 1 all over the square root of 1 minus 10 to the 2nd all over 10 to the 17th. Now that's 17 on the bottom and the 2 on top. There's another rule that we have in algebra where I can say where 1 all over x is equal to x to the negative 1. In other words, anything that's on the bottom, that x, is really to the first power. Whenever I take powers and I go above or below the dividing line, I simply switch their sign. So I can do this. Gamma equals 1 all over the square root of 1 minus 10 to the 2. Take that 17, which was on the bottom, bring that up top. So that would be 10 to the 2nd and then I have 10 to the negative 17 up there. Another rule that we have in algebra is where if we have x to some exponent, x to the n, and I'm going to multiply by x to the m, I can say x equals n plus m. That's where I'm getting this. In other words, gamma is going to be equal to 1 all over the square root of 1 minus 10 to the negative 15th. Remember, I rounded just a little bit. I'm going to move the camera again. We'll take our gamma back up here. Gamma equals 1 all over square root 1 minus 10 to the negative 15. So we should have a little aside from that. We shouldn't call these proofs because they're not really exhaustively proving anything. But what do we mean when we have numbers that are to the negative power? Let's just write this out. So let's do a little aside. A couple different ways that we can play with our numbers. So if I were to say 10 to the negative 1, as we already found out, I can rewrite this as 1 all over 10 to the first, which is also 1 all over 10, which we all know is simply going to be 0.1. So 10 to the negative 1 is going to be 0.1. Down here we have 10 to the negative 15. So we got to figure out a pattern here. Or I could put this into a calculator. Maybe that would be easier. Let me take out my calculator. And I'll just put this in here. So I'm going to clear this. 1 minus, and that would be 1 EE negative 15. So I have one number minus the other. And whenever we have one number minus the other, we get a smaller number. But I don't. I get the same number. Maybe I need a more powerful calculator. Let me go grab one. I'll clear this and I'll take 1 minus 1 EE negative 15. And when I do that, I get the number 1 again. And this is really what we wanted to point out, is that we like to think these calculators are going to give us the right answer. In other words, if I had an object and then I subtracted something from it, I would end up with something less than what I started with. That's what subtraction is. But when we literally do these numbers and we get 1 minus something, you would expect it to be smaller than 1. But our calculators say it's the same thing. That's really odd. For instance, if I had 2 golf balls and I take 1 away, minus 1, I end up with something different than what I had before. This lets you know that we are in kind of an interesting place with our math. Our calculators aren't going to be able to do this, so we're going to do it ourselves. So let's just see if we can pick up a pattern, because I know 1 minus something is going to be less than 1. 10 to the negative 2 would be 1 all over 10 times 10, 10 twice, which is going to be 1 all over 100, which equals 0.01. I'm already starting to see a pattern. If I have negative 1, I don't have a 0 after the decimal. Negative 2, I have 1 0. I'm going to predict right away. I'm going to say 10 to the negative 3 is equal to 1 all over 10 times 10 times 10. 10 3 times, except it's on the bottom, which is 1 all over 1,000, which would be 0.001. I think I have the pattern. So if it's -3, I get 2 zeros. If it's -2, I get 1 0. So that -15, I could say, therefore, 10 to the -15, I'm not going to bother writing all this. I'm going to say it's going to be 1 less 0 than the number that I had. So it would be 14 zeros and then a 1. Zeros and then a 1. So when your calculator lets you down, sometimes you have to go back to doing it old school. So I'm going to put this up there. All right, so now that I've got that, I'm going to take it over here. I'm running out of room down on the bottom. What do we mean? I'm going to move the camera again. I'm going to try and put this into my calculator. So let's see if it'll handle that. 1 minus 0.12. 8, 9, 10, 11, 12, 13, 14, 1. And it gives me 1 again. Again, the calculator lets me down. So I'm going to have to do this by hand. And this is good for you anyhow. Playing with numbers allows you to figure out what they're actually saying. So let's figure out what this is going to be. I'll do another aside. While it seems like I'm kind of doing a proof, I'm not sure if it's going to work in every case. But either way, I picked up the pattern pretty quickly. Let's see if we can do another aside. 1 minus 0.1. Well, that's going to be 0.9. Let's do 1, and let's put a 0.01 minus 0.01. That would be 0.99. I'll just double check myself, make sure that I'm not doing something wrong. 1 minus 0.01, 0.99. I'm already seeing a pattern here. Every time I add a 0, I add a 9. Let's see if this works. 1 minus 0.001 equals 0.999. If that's the case, and I had 14 zeros here, I should end up with 14 nines. So I could put, therefore, 1 minus 0.0023, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 zeros, and then I'd have a 1. Well, that should give me, is equal to, I'm going to put the number underneath. I should expect the, let's see here, if I had 1 0, 2 nines, 2 zeros, 3 nines. So I would expect now 15 zeros, 15 nines. So 0.9995, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I need to put that up here. So it's 1 all over the square root of 0.9994, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 zeros, or 15 nines, I should say. All right, so now I already know that my calculator is not going to give me this answer. I'll just try and put it in anyhow. I already know what it's going to tell me. So, square root of 0.999999 gives me 1 again. So, I can't rely on the calculator, so we're going to do this by hand. So, let's move us over a little bit more. All right, so let's do another aside. Let's do the square root of 0.9. Let's see what that gives us. I'll just use this old calculator here. Square root of 0.9 equals 0.9486. Let's do the square root of 0.99. Let's see what that gives us. I'll hit clear. Square root 0.99. Now I get 0.9949. You could see that this is really rounding to a 9. So 0.949949, and I added another 9 in front of it. Let's try another one. Square root of 0.99, because I've got 15 of them now, so let's try that. Clear? Square root of 0.999. And that gives us 0.99949. So I had 0.949, 0.9949, 0.9949. So let's do one more just to make sure. I'm going to predict that it's going to be 4 9s now. So if I had 1 9 here, I'd have 1 9 here. 2 9s, 2 9s, 3 9s. So I think it's going to be 0.99949. Let me try that out. Square root 0.99999, and I get 0.99949. I feel pretty confident I can put, therefore, the square root of point, and 15 of these now, I think is what we said. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 would be an equal number of 9s is what we said. So I'm going to put the answer down below here so I don't run out of board space. That would be 0.99999. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 4, 9. So that's a 4. Let me make that really clear that that's a 4. Okay? So that is what I'm going to end up with here. So it's going to be 1 all over this value right here. 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And all of this is giving me my gamma, which I was looking for. I got to move this over a little bit more. All right, so what is 1 divided by 9? Because my calculator is not going to be able to handle it again. I'm not going to fall for that. So I can do another aside. I could say 1 all over 0.9. So let me do that. 1 divided by 0.9 equals 1.11. And they're just repeating from here on out. 1.1111. Let's do 1 divided by 0.99. So let's see if we can pick up the pattern. Because my calculator will not do this for me. 1 divided by 0.99. And that is 1.0101101. I think I've got that right. 1, 2, 3, 4. Okay, let's see if we can pick up the pattern. 1 all over 0.999. Let's see what we get there. 1 divided by 0.999. So this is going to be equal to 1.001001001. All right, I think I'm picking up a pattern here. We're going to have no zeros, 1 0, 2 zeros. Let's try 4 9s here. I think we're going to have, this is what I think it's going to be, 1.0001 and then 0, 0, 0, 1, and so on. Let me see if that works. 1 divided by 0.9999. That's going to equal to 1.0030130 I think we can pick up the pattern. I need that because I've got 15 nines that I have to deal with. So if I have 4 nines, I'm going to end up having essentially 1 less than the number of nines. Before I can see that there's a difference, that 1 does not equal 1. So I can put therefore 1 all over 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 is going to be equal to, I think I'm going to have 14 zeros and then 1. And then 1. Our calculators can't handle a number like that, so we have to do it by hand. It's no wonder that Einstein was thought to be a little bit kind of crazy in saying that time dilations. No one could see anything like this. At 10 meters per second, you would only have a factor out to, 14 or 15 places before you could even see a 1. So, in the real world, arithmetic isn't as straightforward as we like to think. When our calculators can't even calculate the precision that we need to be able to see the effect, that's kind of wow. What all this is showing us, and this is an awful lot of work, getting us to this idea that there's a limit that we approach. And that's something we'll have to investigate later in this series. So that's our quiz for today. But the big picture here is play with numbers. Learn to see what kind of patterns you can see. And also remember, when Einstein was doing his work, he didn't have a calculator. And maybe that's a good thing, because if he did, he might say 1 minus a number, oh, it's still equal to 1. It's not, right? We end up having values that maybe we just can't do relying on our machines. All right, that's our quiz for today.